So the next topic and one of our last topics for this course is shear and moment in beams. So again, let's have an introduction. So let's consider first the types of beam that we have. Beam being a slender bar that carries transverse loading. So we generally have three types: your simply supported, cantilever, and overhanging. So for a simply supported beam, your supports are pin and roller. So we already know that, pin and roller. For a pin, there's always parallel and perpendicular reaction depending on your load. And then for a roller, there's only perpendicular reaction. It cannot support horizontal forces. And then we have a cantilever beam, rigid support and free end. So we have here a rigid support. It's not going to allow rotation nor a movement. So meaning here, it's going to resist moment. And then we have there's no support here since this is free on this end. So that's a cantilever beam, supported on one and free on the other. And then lastly, we have overhanging beam. When its ends extend beyond pin and roller support. So for example, here, this is your pin and roller, you still have beams on the edges. But the reason we're discussing this is we need to know the types of reaction present in our supports. Now let's talk about the load. So we have concentrated load and distributed load. Concentrated load, also known as point load, is the approximation of a force applied over a very small area, hence to a point or point load. Next, distributed load, force applied over a finite area. So we also call this a line load. So it's a distributed load that acts over a very narrow area. And then it's in terms of intensity, W, and it is expressed as force per unit length, which is Newton per meter or pound per foot. So you're familiar with this already. So concentrated load are your F1, F2, etc. Distributed load are the ones with your W with a continuous parallel line for forces. Okay. So that was the introduction. So keep those in mind, your beams and forces. Because we're going to use that in our shear moment equations and shear moment diagrams. So let's start. The goal of beam analysis is to determine the shear force V and the bending moment M at every cross-section of the beam. And then to do that, we'll create what we call shear moment diagrams. These are visual reference of the internal forces in a beam. So why are we looking for that? We need to know the shear force and bending moment within your beam because that tells us its strength. Okay? Meaning, will our applied load create a shear force that will cause our beam to fail? That's why we need to know these internal properties. So shear force and bending moment. And then this is our sign convention. So positive, if your shear force tends to bend element clockwise, and then positive also if bending moment that tends to bend a beam element concave upward. So anything other than that is negative. To better illustrate, okay, you have your shear force bending moment for positive and negative. So to simply remember positive shear force if this is creating clockwise movement. Then as you can see here, this is counterclockwise, so negative. For bending moment, okay, you have moment at each end of an element. It's positive if it creates a smiley face. Okay, so for example, if you imagine your force going to this side, causing this side to go down, your beam will form a smiley face. So that's positive. And then a frowny face for negative. Okay, so that's our sign convention. Let's have an example to show you what I mean. So number one, the simply supported beam in the figure carries two concentrated loads, so 14 and 28. Derive the expressions for the shear force and the bending moment for each section of the beam. So expressions means equations. So I need equations for shear force and bending moment at each section. So we have section here, AB, BC, and CD. Those are our sections. And then next, draw the shear force and bending moment diagrams, and then neglect the weight of the beam. Okay, let's solve. Okay, so this is what you do for if we're trying to get equations for each segment of a beam. So I'm gonna first do this, okay? I just want guidelines so that my segments look uniform. Okay, so let's start first for section AB. As you can see, there's already the cut here, that's cut 1. So let's isolate. Now, as you can see, reactions are already given, so I don't need to solve for that anymore. But we already know how to solve for reactions, so it's not a problem. So I'm gonna cut here, right, at that side. And then continue on with our beam. Actually, let's make it more obvious. Okay. So this is your RA, or 18 kilonewton, and I've cut it along this side. And then you're gonna assume direction of your shear and moment forces. Now you can just make a random guess, or you can make an intelligent guess, up to you. Since I have a force upward, I'm gonna guess that my shear reaction would be downward. Okay? And because each segment should still be in equilibrium. So downward shear force. Let me just fix this. So 18. And then moment. So this force will create a clockwise moment. So probably my internal bending moment would be counterclockwise. So draw that as well. So you have counterclockwise here for your moment. And then this distance is distance x from the support. Okay? Then next, if you want to isolate the right side, what you do is remember your Newton's law, or like just method of members. When you assume direction for one end, okay, the connecting member should be the opposite of that. So this is a connecting member. So shear force downward here. So here it should be upward. Okay. And then here, moment. So opposite of that would be this. Okay. So this is your M. And then your applied loads. This is your 14. This is our 28. And then 24. Okay. So now you have a choice to either isolate the left or right side, whichever is easier. So let me just write 3, 2. So obviously here the left side is easier, right? So I'm going to isolate that. So ignore this portion. So to get the value of shear force, we're using equilibrium equations. So summation of forces vertical, or y, equals 0. So positive 18, negative v, equate to 0. So therefore v equals 18, unit is kilonewton, positive, therefore correct assumption, my v is this way. And then the governing sign convention for shear and moment is what I showed earlier. If it creates clockwise movement along your beam, it's positive. So let's see, let's rotate this about our beam. As you can see, that's clockwise. Therefore, for, again, positive, correct assumption, this is clockwise. Okay? And then let's do the same for moment. So this is the first equation. Now take note, this equation can only, or is only true if our x is within 0 and 2. So within this range. So again, that's 0 to 2. So let's write that. This is for x greater than 0 but less than 2. And now let's do summation of moment equals 0. So moment about where you cut. So rotate 18, that's clockwise. So 18 times distance x. And then this is counterclockwise, your moment, negative m equals 0. Therefore, m is 18x Positive, therefore correct assumption. And then to get the sign of this, okay, you'll see if it creates a smiley face or a frowning face. So let's isolate. So this is your moment, right? So it's gonna push down here, and then it's gonna be accompanied by another moment here, okay, to push it down. So as you can see, it creates a smiley face. That's why it's positive. So unit of this is kilonewton, and then meter, then this is positive. And next, let's move on to section B, or sorry, section BC. And then for this, our range for x is in between 2 and 5. Right? So x greater than 2, but less than this total length, which is 3 plus 2, so 5. And then let's draw again. We're going to cut here. Let's apply our forces. We have this 18. Here there's 14. Here there's 28. And then 24. And then your distances. So we have 2 here. This also 2. And then shear force. So we're gonna assume again direction of shear force. I'm gonna guess it's downward once more. Why? Because this is 18, this is 14. I need another downward force to create equilibrium. So that's why I made shear reaction as downward. Next for moment. So 18 creates a clockwise moment, 14 counterclockwise, 18 is larger. So I need another counterclockwise moment to counter that. And then to apply it on the next member, on the connecting member, just do the opposite. So this is V, and then this is your M. And then X is the distance from this end to this end. And again, use moment, equilibrium equation. So summation of forces Y equals 0, 18 minus 14 minus V equals 0, solving for V. That's 4, right? 4 kilonewton. Positive, therefore correct assumption. Right, again, let's rotate this about our left side. That creates a clockwise moment or movement, therefore positive. Then moment, so that's our answer here. And then moment, 18 times x. And then 14 is counterclockwise, so negative 14. And then the distance of 14 to this side is x minus 2. So x minus 2. M is counterclockwise, so minus m equals 0. Therefore, m, simplifying, 18x minus 14x, that's 4x. So 4x minus 14 times 2, 28. Negative times negative, that creates a positive, so positive 28. Again, unit kilonewton meter. Now check, for all values of x, will this be positive? So to do that, as you can see, your range is 2 to 5. There's no negative there, so whatever you put within that range, your final answer will be positive for this moment. Therefore, correct assumption. And my assumption is like this, right? This moment will create a force there, and then this will smile. So therefore, positive. And then lastly, let's create for the last segment. Let's do that. Okay. So lastly, create a cut here for segment CD. Okay, CD. So I'm gonna cut here. So yeah. Again, apply your external forces. We have 18 and then 14 and then 28, 24. Then distances, this is 2, 3, and then your reactions. So I have 18, then 14, 28 downward. So that's going to be greater than 18, right? So therefore, I need an upward reaction to put that into equilibrium. So I'm going to make this upward. And again, that's your V. And then moment. Okay. So for this portion, it's hard to determine if this creates a positive moment or not, or if I need a counterclockwise or clockwise moment. Okay. So you can solve, but this is still just X. Okay. So that's X. So if you're unsure, you can just guess, okay? Because it's the same as our solutions in the previous lecture. Wherein if you get a negative, you still get the correct magnitude. It's just different sign. So if you assumed incorrectly here, you can just correct your mistake. So I'm gonna guess this is clockwise still. Now if you don't wanna guess, to make things easier, you can just look at this portion. Okay? This is gonna create a clockwise moment. Sorry, this is going to create a counterclockwise moment here for the right side. Therefore, I need a clockwise to counter that. And again, for connecting members, should be the opposite sign. So there's already clockwise here, so this is going to be counterclockwise. Okay? So you can do that if you don't want to guess. Okay, so now we have these. So moment. Again, opposite. This is upward, therefore here it should be downward. And then you have a moment here. Okay, now let's create our equations. I'm gonna isolate the left side just so that we're uniform in our value for x. So summation of forces y equals 0, 18 minus 14 minus 28 plus b equals 0. Please solve what's b. Correct, Sierra. 24. Positive, therefore correct assumption unit is kilonewton, and then your v is upward, rotate that. That creates a counterclockwise movement about your isolated segment. So therefore, this is negative. And then finally, summation of moment equals 0. So this is 18 times x, right? Then minus since counterclockwise. 14 times distance is x minus 2, right? From this end. Then minus 28, x minus 5. Then counterclockwise m, so minus m equals 0. Solving for n, you get 18x minus 14x minus 28x, you get negative 24x. Negative 14 times negative 2 plus negative 28 times negative 5, you'll get positive 28. Positive 168. Unit of this is kilonewton meter. Next, check if your answer here will be positive or negative. So to check, remember, we have a range for our segments, and I didn't write it. So our range here would be along this part only. So it's x greater than 5, but less than total length 7. So 5, 7. Okay? And then try inputting any value between 5 and 7. You can choose the greatest number, 7. Sub 7 here, negative 24 times 7, that's negative 168. Negative 168 plus 168, you get a 0. So you can't choose any number greater than that since that's already the upper limit. Therefore, there's no value for x that will create this or will make this negative. Therefore, the answer here is positive. Correct assumption. And then my assumption again is this way. So it's going to create a smiley face. So this is positive. Okay. And that's how you create your shear moment equations. Now we're looking for shear moment diagram. So how do we do that? I'll draw it here. Let's try moving this more. So to draw your shear moment diagram from your shear equations, you'll just draw the equation. Okay? So let's start at 0. This is for shear. So the shear equation for segment AB from 0 to 2 is just a line. That's 18. So that's just a straight line at 18. Okay? Next, again, we're starting with shear. For segment BC, which is greater than 2, less than 5, our equation is 4. So again, that's another straight line. And then next, for the last segment, our equation is 24, but it's negative. So that's the reason why we have the sign. Positive means it's above the 0 point or 0 line. Negative means it's going to be below the 0 line. So we have this, and then this is negative 24. And again, 0. Okay, so this is our diagram. Now to do the shear diagram, moment diagram, like this. So once again, draw the equation. So the equation here for moment for the first segment is 18x. 18x is a line, right? So let's draw a line. And then you want to know what this value is. So to get that, that's just 18 times distance x. And our distance x is 2. So 18 times 2, this is 36. Okay. We're starting at 0 because we're starting at x equals 0. Subs that here and 18x, this is still 0. Right? Next, we have 4x plus 28. So that's another line. Okay. And then to get the value on this point, because I need to connect that, just sub in the value for x here, which is 3 plus 2. So that's 5. So what's 4 times 5 plus 28? Anyone? What's 4 times 5 plus 28? Because we're going to sub 5 into this equation. Correct, it's 48. Correct, Julia and Audrey. Enrique Solomon. Who else? Nina, so Flores. Okay, it's 48. So I'm going to increase this to 48. Then next, we have this. So again, that's another line. And then to get the value at this point, you're going to sub your total value for x here. So now x is from the leftmost side is 2 plus 3 plus 2. That's 7. So please sub 7 here. What's the answer? Negative 24x plus 168. Correct, Trinity? Who else? Correct. Nina. Torres. 0. Okay. So 24 times 7 is also 168. So this becomes 0. And that's how you draw your moment diagram if we're only using equations. Okay? So that's it. That's the example for shear and moment equation and then creating a diagram out of that. Any questions? For number 1, please answer in the chat. Okay, good. So I'm only going to give you one example because that is not the way that we're going to do shear and moment diagrams. The method that we'll use more often is the area moment method or area method. So we'll focus on this. So for area method, let's talk about what happens when you have a distributed loading. So consider a beam that is subjected to a line load of intensity W sub x. Okay, so this is a uniform shape. So to get the value for weight, for uniformly distributed weight, and for shear stress, you use differential equations. So we're going to separate a very small segment here. Upon separating, this portion is your load. Okay, so it's very small, so you can create it as a point load now. Since it's very small, it looks like a square. So area of a square is just base times height, or area of a rectangle is base times height. Since this is a very thin segment, base is just dx. Again, differential x is a very small number, so dx. And then height is your w. That's why the point load version of this is w dx. And then it acts at the centroid of your shape. Again, your shape is a rectangle, so it's just at midspan. That's why this is dx over 2. Next, these are your resulting reactions, shear and moment reactions. So your shear here is upward, okay? And then you have this moment. And then afterwards, within this, okay, there's gonna be a moment due to this differential load along differential thickness dx. That's why here, for the total moment on the right side, it's m plus d. Same thing with shear, okay? So we have shear force here, and then because of this load, there's going to be a differential reaction. That's why there is dV plus here as well. So in order to get those equations here shown, let's derive. So it's not shown, but to solve for this, you're going to do summation of forces vertical equals 0. Okay, so let's just look here. So positive V minus Wx minus V minus dV. Okay, so that's our summation of forces y equals 0. So let me write that again. V minus Wx minus your V plus dV equals 0. Okay, and then V minus V, that cancels out. You're going to be left with negative W dx plus dV equals 0. And then from this, W is just negative dV over dx. It is also negative. And that's how it was derived. So same thing for shear, using summation of moment now. Okay, so that's our equation. Let's move on to the next topic. So upon using those equations, we can create these theorems. So that's why we went through that. So let's focus now on the theorems. So these are the theorems relating load, shear force, and bending moment in your diagram. So load is what we have first, the given figure. Shear force is this, and this blue one. That's your shear force diagram, and then moment diagram is this, the purple one. So let's look at the relation of each. So load intensity at any section of the beam is equal to the negative slope of shear force diagram. So let's try. Okay. Here. And this is your load. This is your shear. Load is negative slope of shear. Unfortunately, this is a straight line. So there's no slope, meaning between your A and B, there's no force. So it still follows. Okay, so 0, 0, since these are all straight lines, they all have zero slope. So everything in between is 0. Okay, next. Shear force at any section is equal to the slope of the bending moment diagram at that section. Let's check. Bending moment diagram, to get the slope, that's rise over run. So rise is 36, run is 2, 36 over 2, that's 18. And that is the value of your shear force. Next. Difference between the shear forces at two sections of the beam is equal to the negative the area under the load diagram between those two sections. So in short, VB equals VA minus area of your load diagram. Let's try that again. So VB, here at this point, that's B, is equal to VA minus the area of your load diagram. So VA is 18. 18. Again, there's no area here, so that's 0. So VB is still 18. And as you can see, this point is still 18. Okay? That's how you do that. And that's why this is called area moment method or area method, because we're dealing with the area of your diagram. And then, in the same way, the difference between the bending moments at the two sections of a beam is equal to the area of the shear force diagram between the two sections. Once again, let's try. Okay, let's do this MB and MA. So MA equals MB equals MA plus area of your force diagram. So MA is 0 plus area of this. This is a rectangle, so base times height, base is 2. 2 times 18, that's 36. And yes, moment at B is, or the value there is 36. Okay, that's it. Then, shear force diagram is 1 degree higher than the load diagram, and the bending moment diagram is 1 degree higher than the shear force diagram. Once again, let's check. There's no force in between our segments. So the next degree to that is a straight line. Okay. And then 1 degree higher would be a slanted line. Okay. So yeah, that's it. So remember, shear force is equal to force of the first point minus area of your load. Moment is equal to moment of the previous point plus area of your shear diagram. And then what if we have a concentrated force and a coupled? So when you have that, this is what you do. So for a force, so at that point, you have, for example, here F. So for whatever value of shear you've already obtained, you're just going to subtract F directly on that point. So for example, and here, this is already 18, but there's an applied load F here, so 14. We're just going to subtract that. So 18 minus 14, that's 4. That's why this point is 4. Okay? And then for couple, same thing. You're just going to add or subtract. Clockwise, positive, counterclockwise, subtraction. Now, here's a summary of the types of loads that we have with their shear and moment diagrams. Okay, so for this, there's no applied load, right? Therefore, your shear is just a rectangle because there's going to be reaction upward here, straight line, and then reaction downward here. Okay, and then for a cantilever, again, there's only shear load here at the end, and then there's going to be a reaction here to negate that. So going down, or if we start here, going up to the right, going down, again, that's a rectangle. Now we have a uniformly distributed load. So there's reaction here again. So we're going to go upward. And then our line is going to go 1 degree higher. This is a straight line, so 1 degree higher is a slanted line. That's why this is an incline. Next, for moment. So moment, since this is positive, and then this is a straight line, your moment will be a slanted line. So slanted line upward, and then you have a couple here, counterclockwise, so subtract. And then you're going to go upward again. And then here, this is just the area of your diagram. So get the area, start here, you'll have a value for that. And then again, this is a straight line, so the next diagram is a slanted line. Same thing here, your shear diagram is a slanted line, so the next line for that is parabolic line. This is your parabolic line. And next, now we have force at the center. So there's going to be reaction at this point, so you're going to go up, straight line since there's no force, and then subtract the applied load since downward, and then straight again, and then there's a reaction upward. Okay, same thing here, you're going to go upward, and then this is a straight line. You're going to go slanted downward, and then up again. Okay, and then this is almost the same here, but instead of a straight line or slanted line, you have a parabolic line. Then moment of this, so this is positive, so your slope will be upward. And then it turns into a negative area, so slope is downward. And so on and so forth. So it's almost the same. So our takeaway here, if your force is upward, your shear diagram will go upward. If your force is downward, your shear diagram will go downward. Same thing with your moment. If the area of your shear diagram is above your 0 mark, the slope of your moment will be positive. So it's going to go upward. If your area is below the 0 line, the slope of your moment will go downward. Okay, a good example is this. This is up. This is your 0 mark. So positive, so this is upward. Then here negative, so this goes downward. And another thing, to know if you got a correct moment diagram, okay, usually you're going to start at 0 and end at 0. Okay, so let's apply what we've learned in an example. The simply supported beam in the figure supports 30 kilonewton concentrated force at B and a 40 kilonewton couple at D. Sketch the shear force and bending moment diagrams by the area method. Neglect the weight of the beam. Okay, let's sketch. So I need this again. Let's put some color. Again. Now, usually you're gonna apply your lines or guidelines on supports and on the load. So there's a load here, one more here, and another here. Okay, so reactions are not given, so let's solve for that. Okay, so this is your RA, and then RB, RE. So we already know how to solve, that's just moment. So summation of moment equals summation of moment about any of the supports, I'm going to choose E. So E equals 0. Right? So let's start RA. Clockwise about E, so positive. Distance is 4 plus 3 plus 3. So that's 10. Next, PB, rotate counterclockwise, and that is 30. Distance is 6. Next, we just have this counterclockwise, clockwise couple. So you're just going to add your values. So plus 40. Okay, and then RA passes through E, so ignoring that equate to 0. Please solve what's RA. Correct Trinity. And correct Nina. Pero 2 points ka na. Correct Miguela. 14. So 14 kilonewton. And then solve also for reaction at E. So that's just summation of forces Y equals 0. RA minus 30 plus RE. Please solve. What's RE? Again, what's RE? Correct, Miguela. Who else? Correct, Parago. 16. So 16 kilonewton. So let's begin with our diagram. Blue. So draw your zero mark. Okay, so this is my shear diagram. This is your zero. So this is how you do or draw your shear diagram. Start as a support. Your support is upward. So you're going to go upward from your zero mark. And then RA is 14. So this point is 14. There's no other force between A and B. So you're just going to go on a straight line. And then this is also 14. There's an applied force downwards. So you're going to go down. 14 minus 30, that's 16, right? So going down, this is 16. There's no other force, so again, go straight. The shear load doesn't care about couple. So straight. And then here at this end, this is also 16. There's a reaction here upwards, so you're going to go up 16. And then you're going to end at 0. So that means you did the correct job. And that is your shear diagram. Next, let's continue on the moment diagram. So actually, let me write that as well. So VB is 14 minus 30. So that's negative 16. Negative 16, negative 16. VE, negative 16 plus RE. So that's 0. Okay? Now let's go to moment. So we're going to start at 0 again. There's no applied couple here, so that's just 0. Next, your area is above the 0 mark, so your slope here will be upward. And then 1 degree higher than this, so that's just a straight line. Okay? Yeah. And then to get that value, so MB is equal to MA plus the area of your shear diagram. So MA is 0. This is just a rectangle, so base times height. Base is 4. Height is 14. What's the answer? Correct, Miguela and Sierra. Gutierrez and Moon. Yung mga wala pang points dyan, I encourage you to answer. 56. Positive. Therefore, this point is 56. Next, to get moment at D, do the same thing. Moment at D, moment at the previous point. So moment at B plus area of your shear force diagram. Moment at B is 56 plus base times height, 3 times 16. What's the answer? Sorry. By the way, negative area, so this is going to be negative. Okay, so plus negative 3 times 16. What's the new answer? Correct, 8. Okay, correct. Nina Flores Paragua Vergara. Eight. Positive 8. So meaning you're gonna go down also, again, since this is area below your 0 axis, your slope is downward. and then it's gonna end at 8. And then look here, we have an applied couple. Clockwise, you're just gonna add. So this is MB on the left side, right? That's why there's a negative. And then MD on the right side, that's 8 plus 40. It's 48. We're gonna go up until you reach 48. So this is 8, that's 48. And then to get ME, so that's just here, 48. And your area is still below your x-axis or line 0. So 48 minus base times height. Base of this is 3. Height is 16. That's the answer. Correct, VMA and Gela. Vergara and Moni. Zero, correct, 0. So therefore, this line will end at 0. And that's your moment diagram. Okay, so that's number 1 for area method. Any questions for number 1? Please answer in the chat. Okay, so it's just all like that. And then let's try starting number 2. Okay, number 2, I'm just gonna start. Okay, I don't think I can finish the solution for this, but let's try. Once again, you're gonna create a line for every end, and then support, and then start and end of a distributed load. There's also an applied load there, another reaction, a support, and then the end. Okay, first step, solve. Let's solve RB and then RD. Okay, let's try summation of moment about D equals 0. Okay, now what we'll do here, we can convert this to point loads. Okay, so your point load will be directed at this location. Okay, and to get the point load, that's just the area of your distributed load. This is rectangular, so that's base times height or weight times length. So 400, its length is 2 feet. You make sure your units are uniform. And then rotate about D. Counterclockwise, therefore negative, and then get this distance, right, from your point load. So 4 plus 1, this span is 2, therefore this is 1. So 4 plus 1 plus 1, 6. Next, RB, clockwise, so positive RB, perpendicular distance 5. Again, this is our support. Next, 200, your 400-pound force, rotate, counterclockwise, so negative 400. Distance from support B is 4. And then we have this. So same thing, let's convert this to a point load at the center. And then rotate this about D, that's counterclockwise, so negative 200 times total length. So that's 4 plus 2. So that's 6. And then distance of this point load. So total length of this is 6. Therefore, half of that is 3. Right? This is 4. So what's left is 1. Therefore, distance is 1. So times 1. And then RD is at D. So ignoring that, there's no other force, so equate to 0. From this, please solve what's RB. Correct, Julia. 1520. What? Negative 400? Oh, this is negative. Nabura yung negative. Okay, so resolve. What's RB? Negative 400 times 2. Correct, Trinity. So this is 1520. Next, summation of forces Y equals 0. So downward, so again, that's just the area. So 400 times 2 plus RB minus 400 minus area, 200 times 6 plus RD equals 0. From this, please solve what's RD. Negative goes downward. Correct, Audrey? Anyone else? Correct, Audrey Paragua. Enrique Paragua. Nakita na. Nakita na din. Flores, correct. Pascual, correct. Yung sinong di pa 3 points. 3 points ka na din. Pascual. Vergara. Vergara. Okay. Okay, the answer is 880. And then unit is pounds. The next step is just to draw now your shear stress diagram and moment diagram. So I'm gonna leave that for next meeting. 10 minutes na lang. Okay. So if you want, you can try solving for this, then just compare your answers when we solve. So again, I'm gonna end that discussion there. On Saturday, you're gonna have your quiz number 3. So open camera, Zoom meeting, Blackboard, upload your solution. Coverage is torsion. So shear and moment in beams will be for modular exam 3, which will be next week, Saturday. So coverage of that is everything I discussed in module 3. Do you have any questions, concerns, clarifications? None? Okay, please answer in the chat. Do you have any questions so far? Okay. Okay, loud. Alright. Okay. So since you don't have any questions, I'd like you to answer this poll. Please check your poll and please vote. What are you into? K-pop, anime, both, or none? You can answer more than one. Okay, there's two more. We have a tie. Okay, so please vote. One of them should be greater. Dalawa pang di nagboboto. I'm gonna end the recording first.